In this lesson, I will talk about fair ranking, specifically in two-sided markets, why it is important to take fairness into account, and how artificial intelligence can help us be fair. Rankers are the main component in every search engine, from a product search engine that retrieves relevant products for users in response to a query, to a newsfeed app that ranks most important news for information seekers. Conventional ranking algorithms follow the probability ranking principle, which says that items should be ranked in order of their probability of relevance to the query or usefulness to users. However, in online platforms that serve a diverse population of users, this can be an oversimplification because we expect the ranking system to be fair to all groups of users while maximizing the average utility of the list. The problem is that maximizing the average utility can unfairly marginalize minority user groups and make the ranking less useful for minority user groups only to better serve a majority user group. In such a platform, the items compete with each other for exposure to the users, and there is the need to divide this exposure between the items in a fair way. It was shown that maximizing the average utility to the users can be unfair to the items, and that it can lead to winner-takes-all dynamics. We consider ranking problems that involve two-sided markets in which we have producers on one side and consumers on the other side. There are many examples of such two-sided markets in online platforms, from job seekers and employers in a resume database to buyers and sellers in an e-commerce platform. In these two-sided markets, producers or items are competing for exposure, while consumers want to see the items they like. Here, the ranking algorithm is the mediator between these two groups to decide which item is exposed to which user, and it should be fair. Now let's continue with an example. Consider a web service that connects employers to job seekers. In this case, we have 3 male candidates and 3 female candidates, and we have relevance scores assigned to each of the applicants, as you can see in the picture. These scores show how qualified they are for this job position. If we follow the probability ranking principle, we would have a ranking like this, where the male applicants are at the top positions, followed by the females. But let's see what that means for exposure between the two groups. If based on position bias, we assume that higher positions receive more exposure, which is shown in the picture by the yellow bars, we see that the female applicants will get 30% less exposure, even though the average difference in relevance between male and female applicants is just 0.03. And this is what we call winner-takes-all allocation of exposure, where a small difference in relevance can lead to a large difference in exposure, and that is not fair. So let's move to the solutions. The simplest way of defining fairness of exposure between groups is to enforce that the average exposure of the documents in both the groups is equal. Here we have two groups, male and females. We call this demographic parity fairness if we want to enforce the demographic parity constraint. In the simplest case, we will have a ranking like this. Here, color indicates the probability value, and it means how probable it is that we show an item in a position. We want equal average exposure for males and females, so here in each position, we assign equal probability to the male and female applicants. This way, we can make sure that the average exposure of the items in both groups is equal at the end. Compared to the unfair ranking, this optimal fair ranking has a slightly lower utility to the employers because, for instance, there's a chance that we show the best female candidate in the first position, who is not the most qualified applicants based on the relevance scores. But since the qualities of the applicants are not that different, this won't be a problem in this example. However, following this idea, even if we lower the relevances for the female group, we will still have the same ranking, and then the drop in ranking utility will be larger, which is not acceptable. So the problem with this approach is that it's ignorant of relevance. To address this problem, we move to the next generation of fair ranking algorithms, where we allocate exposure based on merit. Merit can be defined based on the use case. In our example, we consider relevance of the applicants as the merit. Following this idea, to allocate exposure based on the merit, or in this case, based on relevance, we can generate such a ranking. Color indicates the probability, and as expected, the utility is lower than when we just rank based on the relevance. But this ranking is more fair, and the exposure is divided based on the relevance. So unlike the previous solution, this ranking will change if we change the relevance scores for the applicants. And as a result, it can guarantee a reasonable utility for the users, or in these examples, for the employers. E-commerce platforms are another example of two-sided markets. I'm working in collaboration with Bol.com, a popular e-commerce platform in which we have two types of users, sellers and buyers. And since we care about all of our customers in both groups, our goal is to make sure that we allocate exposure to the sellers in a fair way, while optimizing the result for buyers in product search. To this end, we use merit-based exposure for fair ranking, and we estimate the merit of each supplier based on its quality. So this way, more qualified suppliers will receive more exposure to buyers. So in another word, we optimize for two different objectives: fairness towards suppliers and utility for the consumers. In summary, I should highlight the fact that ranking items in a fair way is more complicated than just sorting them based on relevance when it comes to two-sided markets, because here we should consider both consumers and suppliers. Also, we don't have a general definition for fairness that works everywhere, so it can be different from case to case. And lastly, there's often a trade-off between fairness and utility, and it's important how to balance these two objectives.